How many times has the sun circled the Milky Way? Why do we think there's dark matter at the center of the galaxy? And have we already contaminated Mars with our Earth bacteria? All these questions and more in this question show. It's time for the question show. Your questions, my answers, as always, wherever you are. Across my channel, if a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Nature Doublethink. Hi Fraser, do you think Mars has already become infected by Earth bacteria on the rovers, etc., as it looks like it's impossible to have a clean spacecraft? So this is actually a very complicated question, and the long answer is that we don't know, but it's almost sure that there is viable Earth bacteria on the surface of Mars right now. NASA and other space agencies have done extensive surveys on the International Space Station. So they have these boxes that are mounted on the outside of the International Space Station, and they can hold samples of different kinds of life forms. And so what they'll do is the astronauts will load up them with the different kinds of life forms, and then they open up these hatches, and then they will just be exposed to the vacuum of space for a year or 2 years. And then they will close them up and they will bring back those samples down to Earth and then see if they can bring them back to life if they still remain viable. And many species die, but there are some particularly hardy life forms, Earth life forms, that can handle that journey. So they know that, say, cyanobacteria and water bears, tardigrades, and there's different kinds of lichens and mosses and archaea and various extremophiles can handle this journey. They can go to space, live in the vacuum, in the radiation, in the temperature changes, in the ultraviolet glare, and then they can come back to Earth and they are still viable. And in fact, they've done another set of experiments where they take those life forms that were on the outside of the space station and they then expose them to Martian conditions. And they are also viable. So they're able to come from Earth, go to space, spend 2 years in space, come back to Mars, and they are viable and could grow. But they require a source of water. So all life on Earth requires water. And on Mars, we don't know of places where there's just liquid water sitting around that a hardy life form could actually be able to handle. So that sort of sets the stage for how durable Earth life is. And so there are absolutely life forms that could live on Mars. So when NASA and ESA and various space agencies prepare missions that are going to go to Mars, they consider where it's going. And then that helps them decide, like, what is the level of planetary protection that they need to enact? And so if they're going to go to a place like the moon or an asteroid or someplace that really there's no chance of there being liquid water, no indigenous species, then they don't really worry about it. And they just build the spacecraft and they send it. But if it is going to go somewhere where there is a certain risk, like Mars, like the moons of Saturn or Jupiter or things like that, then they take the next level of precautions. So what they'll do is they will build the entire spacecraft mission in a clean room where they will sort of make sure that the entire environment, that there's, air scrubbers are removing any bacteria from the air, that nothing can get on the surfaces of everything that they're working on. And then they'll take each individual part and they will sterilize it. They have various autoclaves, ovens that they can heat up to high temperatures. They've got various chemicals they can put on the outsides of these things. They have various materials that they cover them in that are microbe resistant. And so then in this clean environment that has the minimum amount of life in it, they take these parts that have been sterilized and they assemble this thing together, and then they will keep it in a sterilized form when they put it onto the spacecraft, and then they'll send it to their target location like Mars. And one of the things that they do is that they measure the bioburden, how much life is on this spacecraft before they actually send it. And the limit is about 500,000 bacteria spores on the surface of the spacecraft, of the rover or the lander. That's acceptable, is 500,000. And, obviously they don't count them up, but they just do representative samples and get a sense of how much there is. And so it just shows you, like, if you don't do any cleaning, the amount of bacteria on these spacecraft is ludicrous. So absolutely, there are bacteria that are on the surface of Mars, on the landers, on the rovers, that given the right conditions could spring to life. And so the question is, do they get access to the right conditions? And that right condition is liquid water. And so we don't know of any places where there is definitely liquid water on the surface of Mars. There are some places that are suspected, but they're very far away from the places that the rovers are currently exploring. It's going to be deep underground. It's going to be underneath sheets of ice where there could be like a liquid layer where water is building up. And so far, we haven't gone to any of those places. Once we do, then I think the risk of contamination goes up. And then you have to ask yourself, is Earth life capable of infecting Mars? We know it can survive. It can come out of hibernation and be able to continue on, but it can really thrive in those kinds of conditions and take off and also push out any bacteria or life form that evolved to be in that place. We don't know the answer to these questions, but caution is the key. That as we explore Mars, we want to stick to places where there's very low chance of there being liquid water. When we go to the places that have liquid water, then the level of precautions have to go up another notch to be even more certain. And then you have to think about, if you're going to bring samples back from Mars, what are the reverse planetary protection concerns that you have to be thinking about? So it is definitely a very fraught, careful process that people are thinking a lot about, and the risks could be dramatic. Like, you could infect Mars with Earth life, and then every time you find places where there's liquid water, you're like, wow, there's more Earth life in here. What were the chances? And so it just means that we messed up another whole planet. So we have to take the risk. So right now, I think the chances are exceedingly low because it just hasn't gone anywhere near liquid water. But as we explore, as we spend more time, as people walk around, live in cities on Mars, and they just exude bacteria off their bodies, then the risks definitely go up. Early rains. When do you think that we will discover the first intergalactic object? So a couple of years ago, we saw the first interstellar object, and that was Oumuamua. And then after that, we saw the second interstellar object, and that was Borisov. And both of these objects are interstellar because they are moving on an orbit that is hyperbolic. So normally, comets follow a parabolic trajectory around the sun, which means that they go around the sun very close, and they go all the way out, back out to the Oort cloud or out to the Kuiper belt or whatever, and then they come back in. They're trapped in the gravity of the solar system. But with Oumuamua and Borisov, they are on this hyperbolic trajectory, which means that they have enough velocity to leave the solar system. And so from the sun, you're looking at tens of kilometers per second of velocity that's required for you to be leaving the solar system. So I'll give you a good example, because like where you are in the solar system defines the speed that you need. But like from the Earth, like if you wanted to leave Earth orbit and leave the solar system, you need to go 42 kilometers per second. Now, the good news is you've already got 30 kilometers per second of velocity thanks to the movement of the Earth. And so if you're looking to go in exactly the same direction that the Earth is going around the sun, then you already can save yourself that 30 kilometers per second. But you still have to make up 12. So you have to go 12 more kilometers per second to be able to leave the solar system. So 42 if you're passing past the Earth. It's more if you're getting close to the sun. It's less if you get farther out in the solar system. So just sort of set that as a baseline. Now, the escape velocity of the Milky Way is about 400 kilometers per second from the orbit of the sun around the center of the Milky Way. And so if there are intergalactic objects that are passing through the solar system right now, they're going to have to be on hyperbolic orbits, just like Oumuamua and Borisov, but they have to be going at hundreds of kilometers per second as they're passing through the solar system. And then you can calculate that they are going hundreds of kilometers through the solar system, which means that they are on an escape trajectory that's going to be leaving the galaxy itself, and they're going to make their way to another galaxy. Now, do they exist? Absolutely. Like, without question, there are interstellar objects passing. There was a paper that we were reporting on at Universe Today a couple of months ago where people were calculating the number of intergalactic stars that are on escape trajectories out of galaxies. And, some number of stars have come from Andromeda and some number of stars have gone to Andromeda. And so it's kind of cool to think about. And so, if entire stars can make this journey, then you can imagine small bits of of ice or rock can also make this journey cross the gulf between galaxies. And so it's estimated that there's somewhere between here and the Oort cloud, there are tens of thousands of interstellar objects passing through the solar system. And so some number of them have got to be intergalactic, right? Like it's probably not a large number, but some number is. And so when you sort of think about this possibility of, say, panspermia, that it's possible that life on Earth started from Mars, that asteroids bombarded Mars, transferred life to Earth, vice versa. And then you could say, well, but also maybe that could be happening at a galactic scale, that interstellar objects are passing from one star system to another star system and they're transferring life within the galaxy. And in fact, they could probably be doing that from galaxy to galaxy. Like as long as they are within the reachable range, then material could be transferring from galaxy to galaxy, just not very much. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Sponsors get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who's already subscribed, and welcome to our recent newcomers: Jason Sin, Doug Smith, Roma LaBelle, Io Intergalactic Elise, Aaron Platt, and Hillary Helkin. Join the club at patreon.com/universetoday. Christian Desalier. In your interview, Dr. Giovanni Renzi said that we know that dark matter is there when talking about the center of the galaxy. How do we know for sure that it's there? You know, dark matter is an observation, that there are multiple lines of evidence that tell us that dark matter is surrounding the Milky Way in this giant halo. It's not this sort of mathematical construct that scientists came up with to make their equations work. It is the end result of a series of independent observations. You measure the rotation speed of the Milky Way or of other galaxies. They should be tearing themselves apart. You measure the speed of the stars as they are orbiting around in various galaxies, and they should be dropping off in a certain way, but they don't, which tells you that they're probably in a larger cloud of dark matter. But then, as a completely separate independent thing, you do observations of the amount of gravity that is distorting light that's moving from more distant objects. This is gravitational lensing. And so you can map out the way various galaxies and various more distant objects are changed and distorted by the intervening mass. And that tells you how much of a halo of dark matter that is surrounding these galaxies. And so, obviously there's kind of two ways you can go about this. One is, well, you just have to have a new theory of gravity, which is a perfectly acceptable answer. There's many people that think there's a perfectly, one way to explain the existence of dark matter or the observations of dark matter is that, in fact, when we're running our calculations for what the gravity should be, it's wrong because we don't understand gravity. That's fine for the galaxy rotation curves. That's fine for how the stars move around inside the galaxy, but it's not fine for the gravitational lensing observations. It's not fine for the measurements that are made in the cosmic microwave background radiation. And so any theory that has to explain this has to be able to handle all of these permutations. It's got to explain all of the observations. And so MOND, modified gravity, explains some of the observations, but it doesn't explain the other ones. And so it can't be the right answer. It can be a partial answer, but it can't be the right answer. And so the answer that explains everything is that there is some kind of particle, that it would explain why galaxies move in the way they do. It would explain why the stars move in galaxies the way they do. It would explain the observations of the cosmic microwave background radiation, and it would explain this gravitational lensing. The problem is that particle has yet to be detected. But if it is a particle, then it is in this gigantic blob that surrounds a galaxy. It's going to be distributed across the galaxy. And in general, things will concentrate down where there is sort of a more density of objects, where there's higher gravity. And so you would expect to see dark matter at the center of the galaxy. So that's why, it's like the scientific consensus is that there is a particle. It hasn't been detected, but that's the mystery. That's the fun part is, people are going to try and look for it. First you make the observation, then you go looking for it. And so, or try to explain it. And so assuming that the mainstream scientific theory is correct, then there should be particles of dark matter that are at the center of the Milky Way. Karen Buchanan, what, in your opinion, is the biggest event that's going to happen in the night sky this year? The biggest event that's going to happen in the night sky this year is the biggest event that was supposed to happen last year but didn't happen. And that is the nova that's going to go off in T Corona Borealis. We were expecting this nova to go off last summer and it didn't go off. And so now it's overdue. And it gets to the point where you're like, is it scientifically interestingly overdue? And so now it's got to happen this year, right? So I'd say that is the one that is the sort of biggest thing that we can kind of predict. But then the other thing is, and probably by the time people are watching this, so maybe we don't even put this into the show, we'll find out if this new comet is going to be really bright. So there's a comet that's supposed to emerge from the sun tomorrow morning, the 14th, maybe the 15th. If we're lucky, it produced a big tail and it's going to be really cool to look at and could be as bright as Venus, which we haven't seen a comet that bright for 25 years. But we're never lucky. We're almost certainly unlucky. Terry Astrahan, what is the plane of orbits around our sun in relation to the flat disk of the Milky Way galaxy? So if you think of the plane of the Milky Way, right, as this disk, and then you imagine the orientation of the solar system compared to that disk, the orientation is 63 degrees. So, like this. So if this is the Milky Way, then this is the solar system is sort of pointed like this, 63 degrees. And that's interesting. And in fact, when you look at the various star systems that are in the Milky Way, they are at random distributions, right? At random orientations. You know, when we look out and see other star systems, if we were all lined up with the orientation of the Milky Way, then we would see the planets passing in front. And the transit method would be incredibly easy because all of the planets that we would see would all be passing in front of all of their stars. From our perspective, we'd see every single planet that's out there, but we don't. They're all in random distributions and orientations. And you can sort of experience this for yourself when you go outside at night. From where I live, I'm sort of imagining my back porch, the planets follow this pathway across the sky. And so does the sun and so does the moon. Roughly, they follow this pathway. And then the Milky Way crosses, for me, kind of directly overhead and goes from the south all the way over to the north. And it sort of depends on the time of year, but like right now, it's this sort of crossing overhead. And so you can see how the plane of the ecliptic is oriented to the plane of the Milky Way, and you can sort of confirm it with your own eyeballs that if they were lined up, then the Milky Way would be this band behind where the planets move, but it isn't. It's at a totally different angle. KGS, how many laps has our sun made around the Milky Way? So the solar system has been around for 4.54 billion years, and it takes about 230 million years for the sun to complete one orbit around the Milky Way. And so if you do the math, the sun has completed just shy of 20 orbits around the Milky Way. And that's kind of amazing. Like the last time the sun was in this position of the Milky Way, dinosaurs ruled the Earth. And then maybe the time before that, multicellular life was just getting started. And then the times before that, there was just single cellular organisms. And then that's it. So it's kind of an astonishing sort of fact about how time moves and how slowly things orbit and how just enormous the Milky Way is. Rowan, do researchers have to pay to use James Webb? And do you have any idea what the waiting times are like? No, researchers don't have to pay to use James Webb. It's completely free. Same thing with the Hubble Space Telescope. And really, it's the same thing with most major observatories around the world, most space telescopes, missions. You don't have to pay to use them. You have to make the scientific case that the observations that you want to make are worth allocating time from the telescope to do it. So there's a group at the Space Telescope Science Institute, STSCI, and they take in all of the proposals from from all of the astronomers around the world. And like any nation is able to submit a proposal. Any individual can even make a proposal to the James Webb Steering Committee. They look through all of these proposals, they consider it against the science goals that have been made for the telescope, and then they start to allocate time into different tranches. So some amount of time is set aside for exoplanetary research, some amount of time is set aside for surveys of the early universe, and so on, that are dedicated to individual astronomers. But there are also large surveys that are just being done for generic purposes, that, you know, they're going to observe every major galaxy in our neighborhood and produce high resolution images that any astronomer can then use and look at and do their science based on. And so the wait times are forever if you can't make a good case for why your science is worth setting aside some of the time from James Webb. But if the science case that you make is compelling, then the wait time is zero, that you are put into the schedule as quickly as possible. So generally the way this works is that the various telescopes, James Webb, for example, they'll make the call for proposals. They say, we are now accepting proposals to use James Webb. And then they will receive all of the proposals, and then they will look through all the proposals, and they will filter them down based on various criteria. And then they will look at the time that the telescope has available, and then they will schedule those proposals to match up with the amount of time that Webb has. And they'll let all the people know that they were awarded time on the telescope. And then at the appointed time, the telescope will turn and make the observations for that astronomer, and then all the data will be made available for them to be able to study and do their science based on it. So I like the model. Now, I can't even imagine what it would be like if people had to pay to use these telescopes. It's sort of like, this is the telescopes are provided by the governments, by the research institutions, by NASA for the free use of all humanity. Siraj, Florida. So if they don't pay for it, how come the taxpaying community doesn't have real-time data access to the tools that we as a society paid for? I mean, having more people looking at data speeds up discovery. So this is the question, which is, when astronomers from around the world are awarded time on, say, the James Webb Space Telescope or the Hubble Space Telescope, they're given an embargo of a certain amount of time, say 1 year. And that's only for a fraction, like this specific time that's allocated to the specific astronomer to answer a specific question, they get a year. But for the larger surveys and stuff, that data is released immediately and is available to the entire public. And then there are other missions where the data is made available immediately, like all the stuff coming from the Mars rovers, things like that. It just gets dropped onto NASA servers, and anybody who wants can go and download it at their whim. And so the question is, like, why the embargo? And this comes down to, if you've gone to all of the work to make the proposal for something that you're hoping to discover, or some science that you're hoping to do, and then you're awarded time on the telescope to make those observations. And let's say you know where planet 9 is. You've carefully done the math and you figured out, you think you know where planet 9 is. And so then you're awarded time on the telescope, and then you make your observations, and then, your observations are labeled as search for planet 9. And then the information is made available immediately on the internet. And then the entire scientific community is able to pounce on this data. And then it comes down to who can write their paper the fastest. And I don't think whoever can write their paper the fastest is what gets you the best science, right? Because whoever writes the paper the fastest and gets the work out and gets it into archive or gets it into a journal is the one who's going to be the one who discovered planet 9, not the people who spend all of the time to put together the paper, to put together the report, to make the observations. No, it's the person who claims the detection of planet 9 in the James Webb observations. They're the ones who made the discovery. So that's not great, right? And so the same thing goes with all this. And so if the data is made immediately available, then it's going to always be a race. You're not going to get the best science done. You're going to try to get the fastest science done, the one that cuts corners, the one that doesn't do the data analysis as well as the others. And so you need to find this balancing point where you give the people who have put in the work to come up with the idea, who have requested time on the telescope, some amount of time to put their thoughts in order to be able to make this announcement. And I don't think a year is a very long time in the grand scheme of things. So every single observation that James Webb has made in the first about 2 years of its flight so far are now publicly available, and anybody who wants can go and study them to their heart's content. It's just the newest stuff that was allocated to specific people. They have a little bit of a head start because they put in the work. And so there is always this balance. And so again, at the end of the day, the thing that we want, I think, is the best science. We don't want to get 50 papers that are all flooding the scientific community proposing different locations or, for different stuff out of the same data. You want to have the best science get done and then have this argument in this time that comes up. But this is like one position. There's plenty of people that agree 100% with what you're proposing, which is that just the data should be made publicly available and it should just be dog eat dog and just fight. And whoever gets there first is the winner. And there's good defensible reasons for that as well. And the scientific community is split amongst this already. So it's a complicated subject, and I don't think we're going to find a really simple answer. So for now, that's the policy. All right. I hope you enjoyed this episode's questions. There'll be another one later this week. Now, we record this show live every Monday. The time kind of changes, but it is 5 p.m. for some part of the world. Sometimes it's here in my home province on Pacific Standard Time. Other times it's in Europe, and other times it's in Asian time. So you're gonna have to sort of see when the next upcoming live stream is. But these live streams are super fun. They're 2 hours long. I try to answer as many questions as I can during that period, and a lot of back and forth. So check out when the next upcoming live stream is. Now, I'm going to chat about a bunch of media that I've been watching, some great television shows. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Bear Lake Roofing, David Gilton, David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, Sean Sargent, SpiderSwap.io, Stephen Fowler-Mully, and Vlad Chiplin, who support us at the Master of the Universe level. And all our patrons. All your support means the universe to us. So I've been watching a lot of really cool television, and I wanted to sort of share some of this stuff with you. So a bunch of shows that I really like have come back for their second seasons. One is SAS Rogue Heroes, which is on Prime. And this tells the story of the SAS when they first started out in Northern Africa during World War II. And now the new season is all about them helping with the invasion of Sicily. And I really loved SAS Rogue Heroes Season 1. Severance has come back for Season 2, and that's on Apple TV. Season 1 was great. I'm a little, it's kind of a weird show, but also some really cool ideas. So I'm looking forward to see how that turns out. And they just wrapped up the second season of Silo Season 2 on Apple TV. And that was fantastic. Like one of the best shows that I've watched in the last year. So I highly recommend Silo if you haven't seen that already. And then a sort of show that I had crept up on me and I never realized that I was really going to enjoy that. And this is The Legend of Vox Machina, which is on Prime. And this is based on a role-playing group that was broadcasting their episodes, they're live streaming all of their role-playing sessions on Twitch back in the day called Critical Role. And they're all voice actors, and people really enjoyed their work and helped Kickstarter making an animated episode of their story. And they ended up raising so much money that they were able to do a full season of their show. And then it got picked up by Prime, and then Prime ordered another season and then another season. And they've ordered a fourth season, and it's so good. Like not just if you like role playing and fantasy and things like that, but just how good the storytelling is, how good the animation is. Every part of it is great. And my wife and I just sort of tried it on a chance and just binged it. Now I want to go back and start watching the role-playing sessions. So, it's sort of inspired me for my own D&D campaign to sort of add a bunch of really cool ideas. So definitely check out The Legend of Vox Machina on Prime. All right. We'll see you next time.